Next thing we are going to talk about is static equilibrium. Specifically here, we're going to deal with rotational equilibrium. Static equilibrium means the object has no linear or rotational acceleration, meaning F equals ma and the acceleration is 0. So it's not going left and right, up and down, anything like that. And it has no rotational equilibrium. So if you sum up all the torques, which actually equals, and we're going to get into this very soon, moment of inertia times your angular acceleration, alpha, it's not turning. There is no angular acceleration. It's not turning left, it's not turning right. So no angular acceleration, meaning some of the torques equals 0, some of the forces equal 0. We're about to deal more heavily with some of the torques equal 0, just that side of it. Whenever you're doing any of these problems, always make sure you draw a picture and always pick a pivot point or a rotation point. Now sometimes what that point is will be quite obvious. It'll be a fulcrum, it'll be a point attached to a wall, it'll be a spot the thing actually rotates around. But if it's not actually rotating at that time, maybe it's a bridge that's flat there, and so it's not rotating at that time, you'll pick a rotation point. More than likely it'll be one side of the bridge that connects to the ground, so one of the other sides. It's best to choose your rotation point wisely. You can see that. You'll see that as we continue to move through this unit. Find the center of mass, because the center of mass, oh, I skipped one. Choose rotational positive and negative. And it doesn't matter which way you choose. Maybe you choose clockwise as positive, counterclockwise as negative, or vice versa. Find the center of mass. The reason the center of mass is very important is because whatever the object is you're dealing with, yes, there are forces pushing down or up on it, but the center of mass itself can cause a torque because the object itself has mass. So you'll have to deal with the torque caused by the center of mass. Find the distance between the forces and the rotation point for all of them. And actually, I recommend labeling all of this on the picture. Please label it all in your picture. Then sum up your torques equals 0. So torque 1, torque 2, torque 3, all equals your 0 if we were substituting into that equation. Break down to forces if needed, or break down, so torques are going to be, as you learned in the last video, force times displacement, or FR sine theta, right? And so break everything down and then break forces down if needed. Specifically, the most common one that you'll end up having to break down is you'll say, oh, the force that's pulling down whenever this kid is on a seesaw is the force of gravity. Well, that's the kid's mass times gravity. You'll see an example of that, and then that'll let you solve for the unknown. Now, whenever you have objects that aren't perfectly are already lined up, let's say here I've got some sort of plank attached to a wall, linear density ax squared, and it's a 12 kilogram plank. Obviously, it's going to rotate down, or a wheel that now, notice the center of mass here, if it's a perfectly uniform wheel, the center of mass is already off the ledge. Notice the distance there. Of course, it's going to rotate down as well. Now, if you were actually trying to solve this, of course, you'd have force of gravity pulling down on it from the center of mass, and it's going to want to rotate off. And the pivot point that I would probably pick would be right here at the edge of the table in the wheel, because that's the spot it's supposed to rotate around, of course. I mean, it's going to roll right here, down and around. So the radius, or the distance from the pivot point to the force, is the radius of the circle, but that's not the actual thing that we would end up using. Or you could, just remember, here's the angle, sine theta, so you would have torque equals Fg r sine theta, or r Fg sine theta, whichever way you wanted to work that. And that sine theta here, is actually what gives us the component of the radius that is perpendicular to it. So it would just be that piece right here. Notice how that's perfectly lined up there. So just this little piece right there. So in my torque equals force of gravity, because that's the force pulling down, r being the radius, sine theta, this r sine theta ends up becoming the perpendicular component of the radius. And that's kind of the point with torque, is that the force and the radius must be perpendicular to each other. And here's another scenario, right? We just mentioned this. And this would be another important thing where you need to find the center of mass. That's what I'm trying to emphasize here. We would need to find the center of mass. By the way, force of gravity over here would break down into mg. Where is the center of mass? Because that'll tell us how far out we need to go. I mean, let's say this board was, I don't know, let's go 5.0 meters long. How much torque is this board experiencing? Well, that depends on where the center of mass is, which we know from this equation with linear density is not going to be at the very center. It's going to be somewhere over here, probably even further out over there. And the force of gravity is going to act down here on the center of mass. And so then to actually get my torque equals RF sine theta, or FR sine theta, depending on which way you want to write that. I'll write FR sine theta. I need to know the distance r that we're dealing with. Yes, it's at a right angle, but what is this distance right here? Now, thankfully, we've actually already solved this problem in the previous video, where we're going to go through and we're going to figure out where the center of mass is. And so I'm going to actually put all that algebra back in here for you just to remind you of it. And I'm able to use 5 as my endpoint here instead of L because I actually do know the length. It's going to be 5 meters. We need real numbers to actually be able to calculate through with my torque. So the center of mass actually occurs at 3.75 meters on that board, and that gives me everything I need to substitute into the torque equation. Notice how here I exchanged the force for mg because that's what's actually happening here. It's the force of gravity acting on the center of mass, so the force becomes mg. I still have my radius, and sine theta is going to end up going away because that's 90 degrees. Now to come out with a torque that this guy was experiencing of 440 newton meters, that amount of torque trying to swing it down. Now here the torques are not balanced yet. I'm not dealing with rotational equilibrium just yet. I'm trying to demonstrate how the center of mass is actually very important because the center of mass will actually cause a torque. All right, so here's a rotational equilibrium problem. I've got a diving board with a kid, 75 kilograms. That's actually more of an adult weight there. And the entire diving board is 2.75 meters long. The pivot point for this is pretty obviously going to be kind of this intersection here between the board and the support there. So that's going to be my pivot point that I'm going to end up choosing. And from the pivot point to the bolts is 0.75 meters. And it's very important to always choose your distances, or always measure your distances from the pivot point. I'm going to choose the way the board wants to rotate for the boy to be positive, and I'm going to choose the other way for it to rotate to be negative. Now, note, this could actually cause other types of rotation. If someone was pushing up on the board here, if there was a force pushing up, then that would be follow it all the way around a negative. Let me actually draw that out. If someone was underneath applying some force, the torque that you would have to give there is going to be a negative torque because it's coming around trying to make the board rotate in a counterclockwise fashion. So that would end up being a negative torque. In essence, the bad habit to get into that some people have is they'll just declare this side of the pivot point positive and this side of the pivot point negative. But that only works as long as the forces are all pointing the same way, if you will, down. But as soon as you start pointing a force up, it causes the opposite rotation. So think clockwise, counterclockwise for your positive, negative, and make sure to draw it on there. We also need to go ahead and label all of our distances. So this right here, the distance to the boy, is going to end up being 2.0 meters. Now I also have to deal with the mass of the board because the board here does have mass. It does not say massless board. That means center of mass. That means if there was no one on it, normal diving board, if there's no one on it and there aren't any bolts, it's going to flip downwards. So there is a force of gravity here at the center of mass on the board itself. And let's go ahead and label the rest of our forces too. I'm going to have a force caused by the boy. This is force of gravity on the, and I'll label it B for boy, force of gravity on the boy. And I'm also going to have force of the bolts. And the bolts are trying to hold the diving board down. So the force of the bolts is going to come down like this. And the point here, force bolts, how much they have to hold, FB, as opposed to FGB for force of gravity on the boy pulling down there. So the point here is the bolts have to hold the diving board from rotating while the center of mass is trying to cause rotation and the boy is trying to cause rotation the other way. So the bolts is going to end up having to balance out the torque caused by the center of gravity or center of mass and the torque caused by the boy. Always make sure in these problems that you identify which forces you're working with. And a lot of times you will find force of gravity be them. Now, I set this problem up quite nice for us because notice all the angles are going to be 90 degrees. That is not always the case. If you had a ladder, let's say a ladder going up against a wall here, and the ladder's going up like this and a person is standing on it, well, here your angle for force of gravity coming down like this is not going to be 90 degrees, where you might call the rotation point where this thing is going to want to spin downwards against the wall. Maybe you pick this as your rotation point right down here at the bottom. Notice your radius R and your force of gravity is not at a 90-degree angle. It's at some other angle theta. So be very careful. And the problem I did set up, though, 90 degrees, just out of kindness. So now I've figured out where all the torques are coming from. I have a torque from the bolts trying to keep it from rotating. I have a torque coming from the force of gravity on the center mass of the board. That's where all the mass could pretend to live. And I also have a torque caused by the boy standing on it. And there really aren't any other forces being applied to this board. So I have my three torques. By the way, if someone were standing right here at the pivot point, the radius to them would be 0. So it would be 0 torque. So just, any force being applied at the pivot point, torque being 0. So I have three torques that I need to put into my sum of the torques. Next, I write down what all the torques are. I have a positive torque from the center of mass, cm, center of mass, and this is just the labeling notation I choose. You choose whatever labeling notation you want. So for here from the center of mass, I have a positive. Notice it's trying to make it rotate positive going clockwise, trying to make it rotate around clockwise. A positive torque from the buoy, because the buoy is trying to do the same thing, trying to make it rotate clockwise. And a negative torque from the bolts. It's going the opposite way. It's trying to make it follow it around, trying to make it rotate negative. So I put all those down. Next thing that I'm going to do is I'm actually going to break these torques down into the force times radius. So now I substitute in F r sine theta for each one, where the center of mass is being caused by the force of gravity on it, radius to it, which I'm going to have to figure out here momentarily, and sine theta for each one of those. And we can go ahead and cancel out the sine thetas, because if you look at this, all the angles are pointing straight down, so each last one of them is 90 degrees, sine of 91, so don't even need it there. Force of gravity for the buoy pulling down times his distance, which would be 2 meters, and force of the bolts, which isn't a force of gravity, right? That's just how hard they're holding on, times its radius going back the other way. Notice that it is negative because it's trying to cause what I have labeled a negative rotation. Now we're going to need to figure out the distance to the center of mass, and that's actually relatively straightforward. This distance right here, I had that labeled RCM. If I know the entire board is 2.75 meters, divide that by 2, assuming that it's a uniform board, and I come out with 1.375. In other words, this distance right here from the center of mass to the edge is 1.375. And to figure out RCM there, the distance to the pivot point, I know the buoy is standing 2 meters away. So from the edge to the pivot point is 2 meters, so I do 2 minus 1.375. So now I have everything that I need to go ahead and substitute into my equation. The only thing that I need to point out before I start doing that is these force of gravities I'm going to have to break into mass times gravity. So you're going to see the mass of the board times 9.81 go in here, and you're going to see mass of the buoy given 75 kilograms times 9.81 go in there. So really here the physics is all done. We've actually already gotten the torque here all worked out for each one of these, and now it's just algebra. I'm going to add those to the other side and start working the simple algebra. So after going through this entire problem, the amount of force the bolts need to hold are just going to be a little bit north, sig figs, 2,400 newtons. And if we scroll back up, let me just kind of summarize all of these problems. The way these problems work is you have multiple things causing torques. Forces being applied at some distance, some radius r, some distance r from a pivot point that you choose, and sometimes the pivot point, and a lot of times it's quite obvious what needs to be chosen. So you have multiple things applying torque, and you add them all up, making sure that you choose positive and negative, positive, negative. So you add up all the torques, and each torque is a force times a distance away, and if there's some angle between them, like if this force wasn't pointing straight down at some angle, then you'd need a sine theta there. If it's 90 degrees, you don't even need it. Cancels out. Sometimes you have force of gravity, that's mass times gravity, if the force of gravity is what's actually being applied, the force. And so you add up all your torques. Step 1, identify them, label a picture very, very well. That's going to be really critical in all these problems, drawing and labeling pictures. And then you add up all the torques, and you just plug in your force times your distance for each one, sine theta if need be, and then you simply work the algebra.